Okay, so we're going to look at this part of our notes. We're moving on to 3.8, which is higher derivatives. So right now, you guys have kind of mastered the ability of taking a derivative of basically any function that exists. Not only can you take the derivative of any function that exists, but you guys have now taken derivatives of things that are not functions. True or false, you can now take the derivative of a circle. You actually did that twice. We did it in the notes the other day, and then we also did it in your assignment. And another thing that comes up, and this is actually, this is overall a good lesson for people. They do well with it. And it's a lot of great application is first and second derivatives. We call them higher derivatives. So for example, do you remember from the last unit, if we have a position function, do you remember the derivative of the position function? It's the, starts with the V, velocity function, yeah. Remember, in order to get the velocity, you took the derivative of the position function. It turns out that the derivative of the velocity function, anybody? Acceleration. And so acceleration is important. We'll talk about that. But first, let's look at the abstract. Okay, tomorrow we'll get to velocity and acceleration. Today we're going to look at this graph right here. One of these is the original function. One of these is the original f of x. And then one of them is a first derivative. One of them is a second derivative. One of them is a third. One of them is a fourth. They are all related. Okay? All right? What I want you to do is just quick look at it and take just 30 seconds to get your mind going. Which one do you think is the original function? The blue, the red, the green, the purple, or the yellow? Talk among your friends. Go. Which one do you think is original? Go. 5, 4, 3, 2, 1. I've heard a couple people say it. Anybody feel real confident? What's that, Jack? Why do you say blue? Okay, that's a good idea. Jack is correct. That's a good indication that it starts right off there. Okay. The other thing that I'm going to, let me hand these out quick here. There we go. Bree? Sido. Joseph. Okay. So let's go to Jack's thought right here. I want to help you guys even find a more definitive way to know that the blue one is the original function, okay? Sometimes you just have to take a guess, but I'm going to look at the other ones and see if this makes sense to you. Tell me something about the slope of the yellow function. It's always positive. Everybody agreed that the slope of the yellow is always positive, so therefore its derivative will always be above the x-axis. Tell me something about the slope of the red one. It's always, so therefore its derivative will always be above the x-axis. Do you see that? So as you look here, how about the slope of the green one? It's always, so its derivative will always be below the x-axis. So here the blue one right here is an interesting one because it is both above and below, okay, and it's never constant. This one is f. That is your original. Now what I want you to do is, now you know that that's the original, see if you can find its first derivative. One of these is obviously its first derivative. Take about 20 seconds, talk, go. 5, 4, 3, 2, 1. Who's got a good shot? What do you got, Tim? Red is correct. Let's look at what he looked at, okay? Let's focus on the blue, okay? Somebody tell me about the slope here. Tell me about the slope here. It's negative, so it should be below the x-axis. Tell me about the slope here. It's 0 right there, so we should cross over 0, and tell me about the slope here. It's positive, so it should be above the x-axis. Look at all the red is below, then 0, then above. So this is f prime. That was through process of elimination, but really we said that these other derivatives, this is the only one that goes from negative to positive. Do you see that? Yeah. So therefore, we knew red was a derivative because it goes from negative to positive. All the others just stay positive or just stay negative. Now I want you to talk, see if you can find the derivative of f prime. Which one would be the second derivative? Think about the slope of the red. Go, talk. 5, 4, 3, 2, 1. Which one is it not? It's not the yellow because the derivative of the red is always, so therefore the graph should always be above the x-axis. So we know it's either green or purple, and it's going to be the green, and I'll show you why. Okay? Yep. So watch here. How would you estimate, if I pick this point, 1, 1 right there, how would you estimate that slope? It's positive, but it's about 1. And if you look, the green function has a height of 1, whereas the purple function has a height of 2. So you can tell that this one is, without a doubt, the green one is f double prime. What is the, so which one would be f triple prime? Tell me about the slope of the green one. Because it's always below the x-axis, so this is f triple prime. And then, as you look at the purple, that's going to be f quadruple prime. So when you start to look at these on your sheet, you might get confused, and it's okay. But I would encourage you to just pick, if you're ever I don't know where to start, just pick one to start with and try to find the derivatives and see if it works out for you. If it doesn't, then pick a different one and try to work through it. But we'll take some questions on that tomorrow, I'm sure. Flip it over. So our goal is to get through these 5 problems today. What we would like to do is find the first and the second derivatives. There are times when we find a third derivative. Doesn't happen that often, but we really do like to use a second derivative test. Second derivative is just as helpful as the first. So let's just practice that. What's the first derivative? Good. Now, we'll do the new thing for today, which is to take the second derivative. And so we put 2 tick marks instead of 1. Now, just to be clear, did we all talk about the other day how dy over dx, how that's the same thing as f prime or y prime? The notation that's used if you take a second derivative in this situation, they put a 2 up there. Okay, so they just put a 2. That means second derivative. You'll see that on the AP exam, and when we get there, don't be confused about. I will always just use the double prime with you guys. Okay, so this derivative is what? Good. That's it. Derivative of the derivative. Yep. Okay, what do I do to take that derivative? The chain rule. Folks, let's all try to do this without the use of the boxes. Can we try without the boxes? What's the derivative of the inside? 2. What's the derivative of the outside? 5. If you multiply those together, you're going to get 10. So 10 times 2x minus 3 to the 4th power. If you have to set up the boxes, that's fine, but just notice how I did the derivative of the inside was 2, and the derivative of the outside was 5u to the 4th. And I multiplied those together, I just plugged the u back in. See that? Okay. All right, so we're going to do this second derivative now, f double prime of x. What's the derivative of the inside? 2, and then the derivative of the outside will be 40u to the 3rd. So you can see you're going to get 80 times 2x minus 3 to the 3rd power. Whoops, should I rewrite it? I'm going to use the boxes for letter C. I just want to see if people were connecting without the boxes. Yep. The boxes are kind of a comfort zone, okay? All right, let's try letter C. I need to use the chain rule, and I'm going to choose to use the boxes here. What goes on the outside? U to the 1/2. 2x minus 3. We all remember the derivative of u to the 1/2. Good. And what is the derivative of 2x minus 3? Dos, which is Spanish for 2. So now we can write that the derivative, or f prime of x, is equal to, what's going to happen as we multiply these? The 2 and the 1/2 will make 1, so those are gone, and we are left with? Yeah. Yep, 1 over the root of 2x minus 3. So we practiced those derivatives before, correct? Now we want to do the second derivative. So true or false, we need to use the quotient rule now. False. You can use the quotient rule. For me, way too much work. I love the chain rule. I think it's like one of the greatest things ever. And so what is the outside here for the chain rule? Excellent. U to the negative 1/2. Because it's the square root in the denominator, we can write to the negative power. And then what's this? The derivative of u to the negative 1/2. Be careful with that. So I got the negative 1/2 in front. U to what power? Negative 3 over 2. Good. Yep. If you subtract 1 from negative 1/2, you get a negative 3 over 2. And then the derivative of 2x minus 3 is still just 2. So when you multiply those, the 1/2 and the 2 will cancel. What are you going to have in the numerator? Negative 1. And in the denominator, we have u, which is 2x minus 3. And that's going to be to what power? The 3/2. Okay?
How does the 2 with the negative 1/2 cancel?
Because we have negative 1/2 times 2 over 1. And you can see that you get negative 1. It's all right. Thank you for asking. So we've seen some practice of taking derivatives that these all should look familiar. Doesn't mean that they're always easy, but they should look familiar. Everybody agreed? Okay, let's try the next one. Good. Product rule. Thank you. Made my day by recognizing the product rule because that's something we forget quite often. So I have f prime of theta. So I take the derivative of theta, which is 0. No, 1. Okay. Times secant. So I get secant of theta plus theta times, and everybody remembers the derivative of secant. Secant tangent.
Now we have to do it again.
We have to do it again.
Come on.
Okay. Very good. Whoop. So, yep. So let's be careful here, okay? We got to be careful. As you notice, we have the product rule twice, don't we? So I'm going to call this F, and I'm going to call these together G. Okay? What's the derivative of F? 1 times then I will have plus, agreed? So I'm going to use the space below me as I add this. Now I just write F, correct? Which is theta times whatever the derivative of that is, correct? So in order to do the derivative of this, what rule do I use? The product. I will now call that F, and I'll call that G. Hey, I get it. It looks kind of nasty. Okay. So let's just review, okay? Because there's a lot of secants, there's a lot of thetas up here, right? Let's just review. The derivative of secant is secant tangent. Okay, then we move on to this, and as you notice, we say that that's F and that's G. What's F prime? 1 times that, which is right here, plus F times the derivative of that. So that's the only thing we have to do yet is find the derivative of that. Okay, so product rule, derivative of secant times tangent would be, yep, good, secant of theta, tangent squared. Plus, what's the derivative of tangent? Secant squared times secant is secant cubed. Because for secant cubed, we said the derivative of tangent is secant squared times that left alone. Okay? We'll just leave it. Okay? We'll just leave it. Okay? So if I asked this type of question on test, I would say this would be an acceptable answer, and I trust that if the AP exam had this, you guys could combine like terms or factor and do whatever. But let's not spend too much time with that. I just wanted to see with the multiple chain rule or multiple product rules, and does everybody understand if we were to have to find the third derivative, that would be really, really messy, wouldn't it? It would. So some of these situations can get really, really messy when we find multiple derivatives. The last one I'm going to show you today, hopefully you'll see how cool this one is. Most people find this one to be a pretty neat one, okay? So let's see what we can come up with here, okay? Notice this is different because the others are all functions. This is not a function. The fact is this is actually an ellipse. But we can find this derivative, and we're going to use, instead of just normal differentiation, we use implicit, because you have the x and the y. So let's end here. What is the derivative of 9x squared? 18x plus the derivative of y squared? 2y, y prime, and the derivative of 4? 0. Remember, I stab myself in the eye with a fork if we don't put 0 after that on this next test. Okay? All right? Yeah, she saved me last time. All right, so now what do? Great, took that derivative. What do I do, though? Yeah, I solve for the y prime, and so I get 2y, y prime is equal to negative 18x. Divide by 2y. Excellent. That wasn't bad at all, was it? Okay, we've kind of done that before. We do understand now after the previous problem that sometimes derivatives can get a little bit messier the higher we go, right? We're going to do this again, and it's going to get messy for a while, but it really turns out quite pretty. And I want you to be able to see it and be able to wait on that. So here we start. Y double prime. Somebody, what rule do I use at this point? I do use the quotient rule. And the quotient rule says the derivative of the top, which is?
He gets really anxious about it.
I get negative 9 times the bottom. And then I subtract. So the top, good, so it'll be a plus 9x. Y prime. Excellent. Good. Great job. Now, that is a second derivative, but the problem is we have the first derivative in the second derivative. Do you know what the first derivative is? See how we just took the y prime? No, hey, trust me, this works out really, really nice. Trust me. Trust me. All right, so we got to drop that there. So we're going to have y double prime is negative 9y Yeah, so plus, let's see, 9x times negative 9x over y. And that's all over y squared.
Wait, why did you not?
Because this is like 9x over 1. So we multiply this by this. We get that. Okay. That's a complex fraction, isn't it? Got to deal with that. So let's write this as y double prime is negative 9y over 1. Is it going to be plus or minus? Minus what? 81x squared over y all over y squared. Good. You're really close. It only gets better from here. In order to subtract these, I have to have. So I multiply top and bottom by. So I've got a y there and a y squared there now, don't I? Okay. So y double prime is negative 9y squared minus 81x squared over y squared over 1. Multiply by the reciprocal, or as Chadley says, we're going to reciprocate it. Negative 9, Jack Ladley, Jadley. Negative 9y squared minus 81x squared over y cubed. Now, at this point, you're like, well, Gens, you told me that this was going to be really, really kind of a pretty problem in the end. It gets prettier than that. Can anybody see what we could kind of do there? Okay, so if we take out a negative 9, and we are left with then what? And I'm going to try to help you guys. I'm going to write the x part first. So what do we get for the x part? 9x squared.
Minus y
And then
squared over y.
plus y squared, right?
Oh, yeah, plus y squared.
Plus y squared. And that's all over y cubed. Who sees it?
Oh my god. No.
Come on.
You're kidding.
Come on.
Push your rooks.
Who sees it? Folks, here, I want you all to see it. Just pause. I want you all to see it. We're going to give you guys a chance.
It's the original function!
It's the original function! And what is the original function equal to? 4. So what can you plug in for here? 4. So get negative 36 over y cubed. Look at that. Yeah. It turns out that all these kind of crazy hyperbolic functions, ellipses, they all work out like that. They all work out like that. Be ready for that kind of a problem. I want to see that you can take that second derivative. You can do it, okay? Good job. Good job. Okay, yeah, so your homework is going to be higher derivatives. Okay? So, do you have your homework packet? What's going on? Oh, you guys, I forgot to run off your homework. Let me go run that off right now.